using random projections, and it's a joint work by Valsesia, Tiziano, Bianchi, Enrico, Magli, and myself, and it has been funded by the European Research Council under the CRISP grant. So motivation of this work is the following. Every picture can be associated with the camera who shot it using an invisible pattern which is contained within each picture. I will detail more in a few slides. And this allows a certain number of forensic tasks and also applications like, for example, think of a web search engine which can search the internet for pictures taken by a certain camera. The problem with these applications is that these peer-new fingerprints are quite huge in size. And so when moving to a large-scale scenario, it can be hard to store them in a large database. And moreover, the query fingerprint has to be geometrically aligned with the one stored in the database. But usually, pictures undergo some kinds of transformation. For example, rescaling. Think when you upload a picture on Facebook, it is automatically rescaled to the default resolution that the physics allows. So, in this work, we propose a method to deal with both these issues. So, we propose a compact representation of the peer-new using random projections and specific construction of the projecting matrix, which allows, which makes the system robust to picture rescaling. So first I will give some basics about the peer-new, then I will move to the baseline compression algorithm using random projections, and then I will talk about the scale robust construction of this algorithm. So the peer-new, which stands for photoresponse non-uniformity, is due to imperfections in the manufacturing process of imaging sensors. These imperfections affect the ability of each optical detector within a sensor to convert photons to electrons. And the result is a noise-like invisible pattern which affects every image taken by that specific sensor. And the characteristics of this peer-new are the following. It is a multiplicative pattern which has the same pixel size of the sensor, so this is huge in this sense. It contains enough pixels to make it unique for each sensor. So each sensor, each optical sensor, the ones that you find in your smartphones, tablets, webcams, digital cameras, are different from each other. And it's universal, meaning that each different sensor has the peer-new, shows the peer-new. And it is present in each photo taken by the sensor itself, except of course from the completely dark ones due to the multiplicative nature of the peer-new. It is quite stable to environmental conditions, and it's robust to some kind of signal processing. So this is something that really it's easy, let's say, to use to implement those forensic tests I was talking about. So let's see how the peer-new can be extracted from a picture or from a group of pictures. In order to extract the peer-new from a single picture, first we need a denoised version of the photo. So we apply a certain denoising algorithm, which can be any denoising algorithm that you know about, the best one possibly. Then you subtract this denoised version of the picture to the picture itself to obtain the so-called noise residual, which is basically a modulated version of the fingerprint modulated by the image itself. So by dividing the noise residual with the picture, we can obtain an estimate of the fingerprint. If you are lucky enough to have a group of pictures taken by the same camera, you can, roughly speaking, average these estimations in order to obtain a higher quality version of this fingerprint. And this enables a certain number of forensic tasks. For example, we can employ device identification. When a photo is tested against a database of known camera fingerprints, or device linking, which tests whether two pictures have or haven't been taken by the same camera, fingerprint matching, which tests a a set of photos against a database of non-camera fingerprints, or the dual problem with respect to device identification, which is image retrieval, meaning that we are given a query fingerprint and we want to test it against a database of pictures. So how do this system work in practice? Well, you have to collect a database of known fingerprints of camera or of pictures. You have to store them in a database, for example, as columns of big matrix D. And when the system is presented with a query fingerprint, one can test this query fingerprint with each column of the database, for example, using a correlation operation, and see which column has the maximum correlation with the input fingerprint. The problem with this approach is that the peer new has the same size of vertical sensor. The row size of this matrix D is the number of pixels of a sensor, which can be easily the order of magnitude of tens of megapixels, so 10 to the power of 7. And the noise-like nature of these fingerprints makes them very hard to compress using standard transform coding techniques, for example. Basically, they are noise. So how do we deal with this kind of signals when we want to build a large database of these fingerprints, a large matrix D? Our proposal was to multiply this database with a random matrix of IID coefficients with much less rows and columns, which we call the sensing matrix phi. And the result is a compressed version of this database, and with significant dimensionality reduction in the number of rows of this matrix. I will show some figures in the following slides. This is a work that we presented recently in an issue of the Transaction Information Forensics and Security. And this machinery works because, thanks to the Johnson-Lindenstrauss lemma, we can state that the distances between different fingerprints is preserved in this compressed embedding, because the Johnson-Lindenstrauss lemma holds for random matrices, random injections. But one may argue that generating a query time or storing this matrix of IID coefficients may be hard, may be impossible, because this matrix has the same number of columns as the size of the sensor. Our proposal to reduce, to solve this issue, and also the matrix product with the query fingerprint or with the database when we are compressing it or we are updating it, may be too complex to perform. So our proposal is, instead of storing or generating the entire matrix, we can store or generate at query time only the first row of this matrix, and then let each row be the circular shift of the first row. So basically we are using a circular and sensing matrix. This solves the problem of storing or generating the sensing matrix. This reduces the complexity of the product, since we can efficiently perform this operation using the FFT. And there are theorems in literature that guarantee that Johnson-Lindenstrauss lemma holds also for the circular matrix. So a further source of complexity reduction is the following. Instead, what we propose is, this is an optional step, let's say. Instead of storing the real valued coefficients of the compressed fingerprint database, we can simply store their signs. So basically, we quantize each quantity with 1 bit. This reduces dramatically the size of the database in terms of storage. The operation preserves the angles between the fingerprints, even in this binarized environment. And of course, also the matching complexity is reduced since we substitute the correlation, which is sums of products of real values with basically a group of XOR blocks, which is cost zero, let's say, complex operation. slide, we show the regional convergence curves for the Dresden database, which is a database of something like 50 cameras, which is publicly available online. And it has the very good property of having a set of flat field pictures, which are very nice for the extraction of the peer review, and which we use to build the database, and a larger set of natural pictures taken by the same cameras to perform testing. From these pictures, we can see two things. Of course, the uncompressed system is the one that performs better, but we can also see that using 500,000 more or less measurements of these fingerprints performs almost the same. So we have reduced the size quite a lot. Moreover, we can see that the binarization operation causes a penalty of half the measurement, which means that the binarized system using n bits per fingerprint performs the same as floating point database system using n-half measurements. So it's something that we could accept, but as we can see from the table in the lower left corner of the slide, there is a dramatic reduction of 3 orders of magnitude in storage of the storage database. The single precision database of the Dresden set requires almost 2 gigabytes of space in disk to be stored, while the binarized compressed one requires 3 megabytes. So it's something that we can easily think of rescaling to other orders of magnitude. Okay, so this was about the baseline compression system. Now, let's think of this scenario. We have our compressed database in which the compression has been performed on fingerprints taken at native resolution of the sensors, but the system is presented with a rescaled, with the fingerprint of a rescaled picture. So how can we deal with this? Well, our proposal is to use the BCCB matrices, so SNC matrices, so block circulant with the circulant block matrices. I will show in a few minutes that using this kind of matrices allows to map the compressed fingerprint of a rescaled image to the rescaled compressed fingerprint of the original size image. So let's see first what are these matrices. So we generate a small random matrix of ID coefficients, we vectorize it, and use it as the first row of the matrix as before. But instead of letting each row be the circular shift of the first row, we divide the image in blocks and let each block of the first row of blocks circulate within itself. And this is done for the first row of blocks. And then we let each block circulate. The result is a BCCB matrix that, of course, now we need to multiply by the vectorized version of the image, as we did before, of the fingerprint of the image, as we did before. But also in this case, we can do it efficiently because it can be shown that the product that I showed before is equivalent to a circular shift of this that small generating matrix which we use to build the big BCCB matrix, and with the 2D version of the fingerprint. And this product can be, again, efficiently performed using the two-dimensional DFTs or IFTs. So this is something that we can handle as well. So now I will explain you how the system works. So let's suppose that we store in the system a matrix, a sensing matrix, which has the size of the maximum optical sensor size that we allow for the system. When a picture is presented to the system, which has this size and x rows times and y columns, we resize the sensing matrix in order to match to the size of the query fingerprint, and we obtain a matrix of random projections. Now we, of course, have to perform dimensional introduction, so we crop it in a predefined position, for example, in the top left corner. And we store in the database both the cropped version of these measurements and also the ratios between the compressed size and the original size of the picture. So this is what this is for what concerns the creation of an entry in the database. Now let's see how the matching operation works. So we are presented a picture, but instead of the original size picture, we are given a rescaled version of the picture. So this is a rescaled version of the picture that we used to build the entry in the database. So again, we resize the sensory metric and the metrics to match the size of the fingerprint. We obtain again a matrix corresponding to the random measurements of this fingerprint, and then we report from the database the ratios that we stored in advance in order to crop the corresponding part in the query random projections. Then we have to compare these two objects, which will have different sizes, so we will have to resize the query random projections to match the ones of the entry in the database, and we can perform the correlation as before. Again, this scheme allows for the binarized version. We simply, at this point, we take the signs of these two objects and perform the Hamming distance. Okay, let's see some performance. Here we plot on the left-hand side of the slide the true positive rate for a fixed false positive rate against the rescaling factor. On the right side, we plot the true detection rate for a fixed false acceptance rate versus the rescaling factor. We can see that the binarized version, which is the dashed curves, perform slightly worse than the floating point ones, but of course with all the advantages that I talked about before. But we can see that there are some dips in these curves. There are some rescaling factors which don't work pretty well. So our proposal to partially solve these issues, yes, thank you, I'm almost done, is to introduce in the database some redundant scales. For example, the default resolution of Facebook, the default resolution of Google+, let's say, to mention two. And we can see that introducing this redundancy helps the system performance quite a lot. These are the regional convergence curves for this redundant setup, and we can see that apart from the smallest scales, all the other ones perform pretty close to the unscaled ones. So to conclude, we presented a system which allows to compress the pure new fingerprints of cameras using random projections, and this allows to reduce the storage requirements and the matching complexity of the system. And we also proposed a method to deal with rescaled fingerprints. Our ongoing work is to deal also with crop, which is another quite common operation. And this is it. Thank you.
Any question?
Have you observed any changes in fingerprints because of the sensor degradation?
Sensor degradation?
Yes, over the years.
Actually, we didn't perform tests. I mean, we used an already available database. But as far as I know, PRU is quite robust. I mean, it's something that it's within the electronics. It shouldn't degrade too much. Or if it degrades, it doesn't degrade in a way that makes the performance different a long time.
Okay, you've got performance there like 90%, that sort of thing. If you're using this for device security to say that I know that this photo was taken on this device, and you've got the ability to have multiple frames, can you combine multiple frames to improve the accuracy of the fingerprint?
Yes, of course. Of course. The best setup is when you have you are given a set of pictures taken by the same camera of flat field, for example, a wall or the sky. This is the best scenario. The more pictures you have, the better the quality. But it doesn't you don't need to have really great numbers. It's enough to have 20, 30 pictures of flat field images, and you're done. You have a pretty good quality of the fingerprint.
So with your technique, you managed to deal with digital rescaling. Right?
Yes.
Now in practice, you have optical rescaling that is known to introduce random bending attacks. Well, not bending attacks onto the PRNU. So how would you cope with this kind of...
By optical rescaling, you mean by zoom?
The zoom of the camera will still be captured with the same sensor. There will still be the same fingerprint.
Yes.
Except that now you have this kind of pincushion effect on this fingerprint. So there have been techniques devised to deal with this, but I do not really see how that would be integrated into your framework.
I'm not aware of. I mean, we didn't try with zoomed images, but of course it's something we should have to deal with. Thanks.
Okay, so thanks. Oh, basically, at the very core of the system, you need to know the rescaling file. Because if you assume that there is only scaling, you know, the original size, you have the current size, and then you have a scale to the current size.
Yes, but
So I guess you say you want to deal with cropped, but you have both cropping
in fact it's a
and scaling, can basically don't know anything.
Yes.
And have the same size, first crop, then size.
Yes.
I
Yes,
guess
you're right.
this is virtually hopeless.
In fact, dealing with crops is really a mess.
If it's croppy alone,
Yes, but you don't know in
because you
advance.
need to know
Yes, but also dealing with crops when you know that the image hasn't been rescaled is a mess. So combining the two together will be messier.
because this is a problem that we had in modern marketing for
Yes,
years, and no solution appeared.
yeah. Maybe we'll find one.
Okay, so thanks to the speaker again.